And with regards to the development of the nervous system, we'll tackle the following topics. We'll talk about the formation of the trilaminar disc and the formation of the neural tube. Those are the embryologic processes of gastrulation and neurulation. We'll talk about the formation of the primary and secondary brain vesicles. And then finally we'll talk about the appearance of the somites and the development of the dermatome, myotome, and sclerotome. Then we'll talk about the peripheral nervous system, specifically the cranial nerves and the spinal nerves. And then we'll go into some anatomy of the cervical plexus, the brachial plexus, the lumbar plexus, and the sacral plexus. So for now, let's talk about the embryologic processes of gastrulation and neurulation. If you go back in your mind to embryology, and you remember those diagrams of those small balls of cells at the blastula stage and then the morula stage, and if you get to about the 14 to 16 day mark, and if you take a cross section through this mass of cells that we have, we see that first we have two cell layers. We have what's known as a bilaminar disc, with the dorsal layer of cells known as the epiblast layer and the ventral layer of cells known as the hypoblast layer. You have the epiblast and the hypoblast layers. We have a bilaminar disc of cells. Well, around the 16th day, at about the midpoint of this cellular disc, we see a depression start to take place or start to develop in the epiblast layer. And this depression proceeds caudally, and it begins at what's known as the primitive node, and it proceeds caudally, forming what's known as the primitive streak. And the primitive streak becomes an invagination of the epiblast layer. And around the 16th day, cells of the epiblast layer in the region of the primitive streak start to proliferate very rapidly, and they start to be pushed down in between a new layer that develops between the epiblast and the hypoblast. And this becomes a new layer known as the mesoderm. And this is the first inclination, or the first sign that we have of a trilaminar disc. And this trilaminar disc eventually becomes the three germ layers, with the most dorsal surface of epiblast cells becoming the ectoderm. The middle layer of newly formed cells becomes the mesoderm, and the most ventral layer of cells becoming known as the endoderm. So the trilaminar disc first starts to make its appearance around the 16th day, and it's at this point that we see definitively the development or the separation out of the three distinct germ layers. Now, about at the 19th day, the most dorsal layer, the ectoderm layer, along the midline starts to thicken. Cells proliferate rapidly, and along the midline, a distinct thickening in the surface ectoderm starts to develop, and this becomes known as the neural plate. Now, as the neural plate continues to thicken and develop, it itself starts to invaginate to develop the neural groove. And the neural groove is nothing more than an invagination of the rapidly thickening neural plate. Now on either sides of the neural groove start to develop symmetrically, bilaterally symmetric accumulations of cells known as the neural folds. And as the neural groove continues to deepen and the neural fold cells continue to develop, eventually the neural tube closes, creating a separate and distinct tube. And it first closes at about the level of what becomes the future C5 region of the cervical spinal cord. And as the neural tube closes, these developing neural fold cells separate from the overlying surface ectoderm, and like the neural tube, which becomes a separate and distinct structure, the neural fold cells become separate and distinct neural crest cells. Now, the closed tube of the neural tube becomes the brain, develops into the brain and the spinal cord, and the opening in the center of the tube develops into the ventricles of the brain and the central canal of the spinal cord. And we'll talk about the fate of the neural crest cells here as we go along. And then, so just to review that now, the neural tube and the neural crest cells derived from the surface ectoderm, the most dorsal germ layer. Now they separate from the surface ectoderm, and the neural tube becomes a separate and distinct structure situated below the surface ectoderm, and the neural crest cells flank the neural tube symmetrically on both sides of the neural tube, again below the surface ectoderm. So they are separate and distinct structures. However, they derived originally from the surface ectoderm itself. And at about the 3 to 4 week period, we have this developing neural tube. It starts to zipper itself closed, and it closes first in the region of approximately C5, the future C5 level of the cervical spine, and it continues to close in a cranial direction, and it continues to close in a caudal direction. And so that at about the 4th week, at the most cranial or rostral level of the developing neural tube, we start to see these expansions within the neural tube. And these expansions become the primary brain vesicles. And there's 3 primary brain vesicles. Proceeding from rostral to caudal, we have the development of the prosencephalon, also known as the forebrain, the mesencephalon, known as the midbrain, and then we have the rhombencephalon, known as the hindbrain. And below the rhombencephalon is simply the spinal cord. Then, as the neural tube continues to develop and it continues to grow, the primary brain vesicles continue to grow and continue to expand, and we see the development now of the secondary brain vesicles. And whereas there was 3 primary brain vesicles, the prosencephalon, mesencephalon, and rhombencephalon, at about 7 weeks we see 5 secondary brain vesicles. So from the primary brain vesicle of the prosencephalon, we see the development of 2 structures. We see the development of the telencephalon and the diencephalon. Now in the adult, the telencephalon becomes the cerebrum, becomes structures of the cerebral hemispheres, such as the cortex, such as the cerebral white matter, such as the basal nuclei, which includes the striatum, the globus pallidus, the substantia nigra, the nucleus accumbens, and various subthalamic nuclei. Also develops into the diencephalon, which in the adult gives us the thalamus, the hypothalamus, the epithalamus, and the retina. The mesencephalon, the primary brain vesicle of the mesencephalon, remains undivided and continues in the adult as the mesencephalon, which gives us the brain stem, which gives us the midbrain of the brain stem. And then the primary brain vesicle of the rhombencephalon divides to give us the metencephalon and the myelencephalon. And the metencephalon gives us the pons of the brainstem and the cerebellum. And the myelencephalon gives us the medulla oblongata of the brainstem. And then below the myelencephalon, again, we simply have the spinal cord. And this is a fluid-lined cavity. There's a fluid-lined cavity of all these structures that is a continuous cavity that gives us the ventricle system of the brain, which is continuous with the central canal of the spinal cord. And so just to review, for those of you that have your handout materials, we see that in our diagram we have a 3-week-old embryo, and it shows the primary brain vesicles simply as extensions of the most rostral end of the neural tube. The primary brain vesicles begin as slight expansions with 3 distinct regional areas separated by bends in the tube. These bends are known as flexures. So we have the prosencephalon most cranially, the mesencephalon slightly below that, and the rhombencephalon even below that. And then at about 7 weeks, due to continued growth of the cranial end of the neural tube, the prosencephalon develops 2 structures, the telencephalon and the diencephalon. The mesencephalon continues to grow but remains undivided. And then the rhombencephalon divides to give us the metencephalon and the myelencephalon. And those are the 5 secondary brain vesicles which then continue to grow. Particularly the telencephalon continues to grow to give us the large cerebral hemispheres, and then all of the subsequent structures in the adult brain, such as the thalamus, the hypothalamus, all the structures of the brainstem, and also the cerebellum. Now, meanwhile, simultaneously, ectodermal cells, again from the dorsal ectodermal layer, are proliferating rapidly. And they continue to push downward into this newly forming middle layer, this mesodermal layer. And they fill this middle layer of this trilaminar disc. And the cells are proliferating quickly, and they pile up on both sides of the neural tube. And this becomes what we refer to as the mesoderm. Now, as the mesoderm continues to thicken, the mesoderm separates out into 3 distinct areas. Closest to the neural tube is what's called the paraxial mesoderm, and we'll talk more about the paraxial mesoderm here as we go. It's the paraxial mesoderm that develops into the future somites. Next to the paraxial mesoderm is the intermediate mesoderm, and it's the intermediate mesoderm that's going to give us the future kidneys and the urogenital system. And then most laterally, meaning lateral from the neural tube, we have the lateral plate mesoderm, also known as the parietal and visceral layers of mesoderm. And it's this portion of the mesoderm that gives rise to the linings of the body wall and the linings of the viscera and the heart, meaning that it's the parietal mesoderm that gives the lining of the body wall, and it's the visceral mesoderm that gives the linings of the viscera and the heart. Then simultaneously, while the neural tube is developing, and for those of you that have the PowerPoint presentation, and recall that the sclerotome is closest to the neural tube, so that's the mesoderm. Meanwhile, back at the ectodermal cells, the ectoderm and the neural tube continue to enlarge and differentiate, and ultimately the ectodermal cells differentiate into the structures of interest to our discussion today, such as the central nervous system. Ectodermal cells develop into the peripheral nervous system. They develop into the sensory epithelium of the ear, of the nose, and of the eye. Eventually gives us parts of the epidermis and the integumentary system, such as the hair and nails. And gives us also the subcutaneous glands, of which we mentioned several of those earlier, including the breast, the glands of the breast. The neural crest cells continue to develop and give us structures also of importance, including all sensory afferent fibers that have their cell bodies in the dorsal root ganglia, of all spinal nerves, and also of cranial nerves 5, 7, 9, and 10. The neural crest cells give us the sympathetic chain, the peripheral ganglia, and also the adrenal medulla. And we'll talk more about sympathetic pre- and post-ganglionic autonomic fibers here as we go along. Neural crest cells give us Schwann cells, and the glial cells in the central nervous system. They give us the melanocytes and give us lots of different structures, all of which originally came from the dorsal ectoderm. And the mesodermal cells give us the sclerotome, the myotome, and the dermatome, proceeding from most medially to most laterally. Well, we won't really talk that much about the sclerotome because less is known about the sclerotome, and particularly less is known about the innervation of the sclerotome, although we'll talk about the innervation of bones and joints later on in this program, and there is some principles to guide us in determining what is the innervation of sclerotome structures. Well, let's talk a little bit more about the dermatomes and the myotomes. So it's the myotomes that give us virtually all the muscle of the body. All of the muscle of the body develops from the mesodermal structures. Now, skeletal muscle, your biceps, triceps, quadriceps, gastrocnemius, all skeletal muscles, they develop from the paraxial mesoderm. Now, your smooth muscle, such as found in around the gut and in the intestines and what have you, those are derived from the visceral layer of the lateral plate mesoderm that surrounds the gut tube, and cardiac muscle also develops from the visceral layer of the lateral plate mesoderm, but this is the mesoderm that surrounds the heart tube. Those are structures that we haven't talked about. I simply mention it here to let you know that all muscles of the body develop from the mesodermal cells. The only exception are a couple of locations where we find smooth muscle throughout the body, such as in the pupil, such as in the mammary glands, and such as surrounding the sweat glands. Those smooth muscles derived from the dorsal ectoderm. All other muscles in the body, including skeletal muscle, smooth muscle, and cardiac muscle, develops from the embryonic mesoderm. Okay, so that's the origins of the muscles, and we'll talk a little bit more about myotomes in a minute. Well, what about the dermatomes? And so a dermatome, let's talk about dermatomes. And the AMA guides give us Also, the AMA guides give us, and I've also provided for. So let's talk about myotomes. So with consideration